All right, so I'd like to end this series on electric and magnetic fields with the most complicated code I have ever used in an introductory physics course. I was originally going to assign this project to my students, and then I said, well, let me try making it first just so I can write the instructions better. And it took me a good couple of weeks to put this thing together. So I decided, okay, I'm not going to have the students build this. I'm going to hand them this code and just ask them some qualitative questions about it. This is a code that demonstrates Faraday's law of induction. The idea that a changing magnetic field produces a current, produces an electric field that creates a current in a loop. So you have to do a few things with this. One thing I had to do was create a subroutine, create a function to calculate the flux through a metal loop. So the way I'm defining this is with 4 arguments. The first 3 are the 3 points that define the loop. So in order to get a rectangle in 3-dimensional space, you need to give 3 points. You have to give a corner, and then you have to give the 2 adjacent pieces, or 2 adjacent corners. The 4th corner is implicit. The 4th corner is entirely determined by the first 3. You only have 3 degrees of freedom with your rectangle. And it's assumed, here's an important note in the comments, it's assumed that point 1 is the corner between point 2 and point 3. So point 1, point 2, and point 3 form an L, and point 1 is the corner of that L. It's the point that the other 2 lines have in common. And then we have a list of sources. This is assumed to be a set of current-carrying objects that have 2 attributes, a position and a current. They can have other stuff, because this is going to be a cylinder or a box or some other object with a length. But this function is just going to access their position and their current. So in order to calculate the flux, we've got to do a few geometric things before we can get to the actual physics. The first thing we have to do is we have to get the basis vectors of this rectangle, meaning these are the vectors that point along one leg of the L and the other leg of the L. This is sort of like if you're working in a lattice, these are like the basis vectors of the lattice. And then we need to get a unit vector that's perpendicular to the rectangle. So we take the cross product of our x hat with our y hat, and that gives us the unit vector perpendicular to the rectangle. This is important because the flux involves the area vector of that rectangle, and you might recall that that's the magnitude is the area and the direction is perpendicular to the surface itself. And then we need to find the center of the rectangle. Fortunately, that's just the average of point 2 and point 3. So that's halfway across the diagonal of the rectangle, making use of the minimal amount of information required by this function. And then we want to make sure that in-out points outward from the origin. This is just to make sure we get the direction of the flux correct. So this is just a little bookkeeping here. And after all of that, we can finally calculate the flux. So we start with a flux of 0, and then basically we do a double integral. We start at one point in the corner, and we work our way toward the opposite corner. And basically we are moving our point along the y direction, and we're moving it along the x direction. So this is like a double integral. And basically for each of those, we're taking the flux as being equal to b dot n hat. So this is the magnetic field that we are calculating at that point, times dotted with the unit vector, because if the field goes parallel to the rectangle or perpendicular to the n hat, it doesn't contribute any flux. If it points inward, we get a positive flux. If it points outward, we get a negative flux. That's why this piece up here is so important. And then, of course, we multiply by the area of that little piece squared. So we're dividing the rectangle up into teeny tiny squares of size dx by dx, and we are adding up the flux through each of those little squares. And that gives us the total flux. And this is, we're now 47 lines into this code, which is usually the length of my entire code. We're 47 lines into it, and we just defined a single function. It gives you an idea of how complicated this thing is. All right, here is something that looks familiar. This is where we create the primary coil in the transformer. So Faraday's law is used to figure out how a transformer works. That's a real transformer out at your house near the power lines, not the more fun kind of transformers. Although the robots in disguise probably do have transformers as part of their circuit components, I'm sure. Here we've got our 4 cylinders to make a coil. We're going to have current going around the coil. It's the same type of setup we've had before. Same way down here, we've got arrows to depict the current in that coil, and that's going to be important because our current is going to be changing. And then here we have something new. We're creating the secondary coil. So the primary coil is the loop of current that we are changing. That's the thing that we as the user or as the experimenter are driving. And then the secondary coil is the recipient of the induction. The secondary coil is where the induction takes place. And so this is the coil that has to go into the flux function that we have at the top of the code. So in order to help me with that, I'm defining this coil in terms of its right front corner, its left front corner, its right back corner, and its left back corner. And just like before, you only have to define 3 of them, and then the 4th one is given implicitly by the other 3. And so we set up our secondary coil. This time I'm just setting it up as a curve. I didn't want to go through the trouble of setting up 4 cylinders because we're just going to set up a curve. It's easier to set up and use the curve function here. I realize that I haven't used the curve function a whole lot in my video, so I am planning a VPython for Beginners tutorial about the curve object a little bit later down the road. And then we need arrows to depict the current in the secondary coil, so we have secondary arrows down here. And we're taking and setting those up along the edges of this curve. And so then we need to start out with the initial flux. So the induced electric field is based on the change in flux. So I always have to have 2 values of flux. I need the previous value of the flux, and then I need the current value of the flux. So this is getting us set up with the previous value. Here we're going to set up some graphs to display the magnetic flux and the induced electric field. So this first one is just the total amount of magnetic flux through the secondary, and this one is the electric field induced in the secondary. And here we've got a visual created for our magnetic field vectors. We are setting up these magnetic field vectors just based on the primary. The secondary is also going to create a magnetic field, but that gets way too complicated to display here. That is something you could have your students add if they really, really wanted to. And then I'm setting up a couple labels so that we can keep track of which is the primary coil and which is the secondary coil. I found that was helpful when my students were completing a few questions based on this activity. I should also mention I'll include a link in the description below to the activity I conducted and the types of questions I asked, just in case you're a physics teacher and this is of interest to you in your class. So here we're creating a circular arc of magnetic field observation points centered around the midpoint between the 2 coils. So that way we've got magnetic field going through the secondary coil. Keep going down here, we've got our time loop. Here we've got our current oscillating. So this is setting us up for a, this is where our current updates. So this is setting us up for an alternating current source, which is what you need to do a transformer experiment. Here we update the magnetic field vectors to display. And here we finally get to the physics. First we need to conduct the new flux. So this is a flux now going through the secondary. We'll update the graph of the flux here. And then here we calculate the EMF. I really hate that term. It's not a force. It's an electric potential, but that's what the textbooks call it. So I go along with it with much protesting. And this is basically the change in flux over the change in time, negative change in flux over change in time. So it's the current flux minus the previous flux divided by the time step. So this is just basically turning a derivative into a slope. We did all of this computer setup up above, and this is really the one key part of the physics is a nice simple slope formula. Here we rewrite the current flux value to the previous flux, because that's going to be the previous flux for the next go around of the loop. And then here we update our arrows in the secondary coil. We calculate the electric field. as being the EMF divided by the total length of the secondary, because electric field is basically electric potential divided by distance, more or less. You can't see it, but I'm waving my hand here. And here we graph the electric field, and we update our arrows in the secondary. So at 149 lines long, this is the most complicated thing I've ever put in front of introductory students, but it really pays off because it really helps to demonstrate what what this induction process looks like. So here we've got the current oscillating back and forth inside the primary coil. And here we've got the induced electric field in the secondary coil. And you notice that they're out of phase with each other. When this thing is at 0, this thing is at a max or min. When this thing is at a max or min, this thing is at 0. That's because they're offset by that derivative. You can also have your students check out the right-hand rule. So when the current's going through, when the current is changing in a downward direction, you get the when the magnetic field is changing in an upward direction, you get the electric field going around this way. When the magnetic field is changing in a downward direction, you get it going around the other way, and it obeys the right-hand rule based on Lenz's law, which is pretty awesome. If I scroll down here, I can see the magnetic flux. This is going like a cosine, because this is basically going to match the current that we had in the primary coil. Then if I look at the induced electric field, it's going like a sine. So it's going like the negative derivative of the magnetic flux. The magnetic flux is at a maximum at 1 second. The induced electric field is at 0 at 1 second. So you can have the students also verify the derivative relationships here. So like I said, my students enjoyed this. I think this helped to illustrate what's going on with this. I had them do this before having them do a Transformers experiment with the Pasco coil sets. So I'll leave a link to that activity that I conducted in the description below. So thank you so much for watching. I will see you next time. Bye-bye.